So today we're going to focus on thinking about flow lines and thinking about how we can solve for head in any given place, that's that total head. If we have some information, how can we solve for that total head in any given space of interest that we have? And so to do this, we're going to have to focus on this idea of what is the Laplace equation. Then that helps us to understand how we can derive equipotential lines and then to draw flow nets in a system. So Darcy's law is great for determining flow through fixed volumes, right? Flow through a pipe. Rarely do we know the distribution of head, though, through an area of interest in the subsurface, right? We only have these wells that give us these peepholes into the subsurface. But if we know total head levels above and below an area of interest, right? So we have boundary conditions on a thing that we're interested in. We can use the conservation of mass, right? That law, the conservation of mass law, with differential equations to determine the distribution of head across space. Differential equations relate one or more functions to their derivatives. In this case, total head at any position as a result of a steady state water flux, meaning that the volume of water flowing through the system in this condition is going to remain the same. So let's begin to think about how we might write out this steady state flux that we have in our system. So right now we're going to take the most simple cases. And we're always starting with the most simple cases, because if we can start with a more simple case, then we can become more and more definitive, right? We can add more to it, but it's always good to just start at the very basics. So let's consider a 2D problem here. Let's consider that we have flow that's happening in the X direction, and we're going to think about that flow spanning across this area, this change in X, that we have flow that's occurring in the Y direction in this system, and that's the length and change of Y. Now remember, we're talking about a box, so if we're thinking about considering a problem of a Q, the change in X and the change in Y are exactly the same, and the change in Z is equal to that as well. So we can take our discharge coming in and our discharge going out, and we can say our discharge is equal to that volumetric flux, or that specific discharge times some area, right? So Q times area. And we can say that our output is that same Q that came in plus any change in Q that may have happened as we moved across that space in X. So as water flowed from here to here, we had this initial Q, and then if any water was added or taken away, that's this part here, what was that volume of water? What was that amount of water? And then out of this area that we have. We can do the same thing for in the Y direction. We can say, here is our specific discharge, here's the area, right? That's what Q is equal to. And then as it moved across in this direction, right, we had the initial Q that we started with, that flux, plus how that flux changed as we moved in the Y direction, multiplied by the area that it was moving out of. Now you can see that there's some terms that are fairly similar in these equations that we could remove, right? We know that our X and our Y are the same. We know that Z is the same. And so we can go ahead and drop these area terms to begin to solve this idea of inputs minus outputs at steady state flow. So our steady state flow here in this condition is we're actually going to say is equal to 0. And so what we can say is that our inputs, right, minus our outputs must equal 0, a change in storage, right? We've talked about this idea of the law of massive conservation. And so if we go ahead and we rearrange this equation, what we actually end up with is a change in the flux over X times X minus a change in the flux over a change in the Y, over Y, over this distance of Y. So at any point along Y, we could start to solve the equation. Now we can then go ahead and again, by this idea of substitution, right? We know that little q, that specific discharge is equal to negative K times the change in H over the change in Y. Or you can say the change in X, because all of these are a cube and they're exactly the same. So we can go ahead and we can substitute this Q into these different locations, and we can end up with an equation that looks like this. Now, inevitably, because this is an isotropic system and because this is, our K's are going to be the same. So K in the X direction and K in the Y direction are exactly the same. So we can say that those K's are the same as well. That we have this change in head and the change in X and change in Y direction, but that change in X and change in Y are the same. And so because it's isotropic and because it is a cube, we end up with an equation where we have the partial differentials of the change in head over the change in space that we're talking about. And so this equation is the Laplace equation that allows us to solve for a change in head at any given position within the boundary of this system. So the Laplace equation describes how energy of a fluid changes as it flows through various media. It is independent of K because we have an assumption of isotropy, right? Flow is not being preferentially occurring in any of the directions. When H is fixed, it can be used to solve for the coordinates of other H's. So these are known as the equipotential lines, right? So we've in class drawn contour lines, right? We call those contour lines when we're talking about water level, we call them equipotential lines. And so we can begin to able to solve that in these systems. Now, equipotential lines plus flow lines actually create what is a flow net. This is a contour map of the total head, which can then be used to determine the pressure, the volumetric flux, and the hydraulic gradient at any given point in that space. These can be approximated using finite difference approaches, or they can be solved using finite element solutions. Now, I'm just mentioning those here, and we're going to dip a little bit into this idea of how these equations might be used later on, or approaches. So when we begin to draw our flow nets, this idea, right, of isotropy and homogeneity underlies it. And what we're going to do is we're going to draw our equipotential lines and then our flow lines. And just like we did in class, our flow lines are always going to cross our equipotential lines at a 90-degree angle or perpendicular. When we draw these, the area between the flow lines and the equipotential lines should form a square element, right? Because what are we trying to represent? This idea of the Laplace equation, essentially, of this cube of the system. The flow channels in the areas in the area between two flow lines, right? So if you draw two flow lines on a system, and we'll give you a depiction of this soon, the area between two flow lines is called a flow channel. And this is where the flow rate in the channel should be the same. So if you are in a flow channel, and we'll look at an image of it, you should have the same flow rate. The hydraulic head drops, right? So as we move from one equipotential line to the next is the same. So if you have, let's say, 3 contours or 3 equipotential lines, each of those equipotential lines may be a drop of 1 foot or 1 meter. Head lines and flow lines must agree with the boundary conditions that are set up. Now, our setups can have different kinds of boundary conditions. Dirichlet boundary conditions are what we call a constant head, right? So always at this condition, at this boundary, it'll be 10 meters high, for example. Then at a Newman boundary condition, this is a constant water flux, but a constant water flux can also mean that there is no flow. So no flow boundaries are another version of a Newman boundary, which is considered a constant flux. So let's take a look at these flow nets. So we're given this example of thinking about a reservoir in a system. And this reservoir has a dam, and you can see the geometry of the dam. And then you can see that we have this isotropic, homogeneous sand material below. And you are asked to solve for the flow lines and the pathways and the discharge that might be taking place in this system. So what we're going to do is first draw in these in our equipotential lines, right? So our equipotential lines, let's say we start at 10 over here and we drop to, let's say, 1 over here, we may be putting in equipotential lines along these flow paths, each of these representing the same head drop. So if this is a half a meter head drop, each one of these lines would then represent that contour. Then when forming the boxes that we're trying, these kinds of squares, and you can see they're not perfect, but these are pretty decent squares, you draw in your flow lines. So here are your flow lines in the system. And then between each of these flow lines, which are in blue, is going to be your flow channels. So anywhere within here, right, if we put a dot in here, we can determine the head distributions. We can determine the volumetric flux, right? So if we were in this spot here, through these two flow channels, we know what the change in head is. We know what the hydraulic properties are of that system. Then you can be able to determine your volumetric flux. We can determine the gradient of these systems, and we can determine pressure at any point in these systems as well, as long as, and as the velocity of your system too, if you know the effective porosity. So the tips for getting into flow nets is going to say you want to use quality paper. You always want to draw your boundary conditions in pen. So let's go back to what we have here, right? Our boundary conditions here, green, what is that boundary? It's a constant head boundary. And over here, we have another constant head boundary. And along this dam and at the base of this impervious surface, we actually have no flow boundaries. So that's the boundaries of the systems that we have. You always want to kind of develop 3 to 6 flow channels. The more channels that you put in the system, the more complicated it becomes. And it's very, very hard to actually be able to draw in all those squares. So depending on your system, right, you want to be able to draw in first your 3 flow lines. You want to draw in your head drops in this system. Now the head drops, or those equipotential lines, are really useful, but sometimes you have to draw in partial head drops instead of partial flow lines to be able to help create the squares that you're looking for. You always want to start with this, drawing it with a pencil. You're going to use a pencil and you're going to quickly kind of sketch where you think things are. Then you're going to modify it. And you're going to continue to try to reorient where your flow lines are and where your partial or where your head drops are until you can get to the best kind of square solution, right? So each one of your flow channels has kind of a square, or not your flow channels, but each one of your flow lines and your equipotential lines really is forming these kinds of square shapes that we see here. Now, once we've been able to do that, what can we calculate? Well, we can calculate our discharge, and we can calculate our change in discharge from any given location. So if we think about our change in discharge here for any given flow channel that we're looking at, we can say that it's equal to the transmissivity. And now this is a new term that you haven't quite heard. Transmissivity is when we take our hydraulic conductivity of a material and we multiply it by the thickness of the aquifer. So we've always used this term in class B to describe thickness, but in the instance of transmissivity, it's discussing the thickness of the aquifer through which water can move. And so our units for transmissivity are length squared per time. So we can put our transmissivity into the system. We can put our change in head at any given location. So like maybe it's between a head drop between 7 and 8 here. And then we can also put in information about the width of each of these, right? So what is the width of your flow channel and what is the length between your different head drops that you have in the system? So once you're able to say, okay, I have a hydraulic conductivity, I know what my head drop is, I know what the width of my flow channel is, I know what the length is between my box, you're then able to go ahead and solve for what that discharge through that area of interest might be. Now, when you want to solve for the overall discharge of the system, what we want to think about is, again, this is kind of taking into consideration the average behavior of the entire system as opposed to one specific point. You're going to look at the number of flow channels. You're going to look at the number of head drops. So in this instance, the number of flow channels as we're adding them up, right, would be 1, 2, 3, 4, 5, 6, 7. So we would have 7 flow channels. And the number of head drops we would have are essentially 10. So we see 10 equipotential lines that are drawn on here. And then we would look at the total change in head. So we'd look at the head from the upstream condition, right? This is our boundary condition on the right-hand side, our boundary condition on the left-hand side. So the difference would be 9. And then you'd multiply that by the transmissivity.